Welcome to section 2.4, where we're connecting the differentiability and continuity idea together. So we're going to determine when do derivatives exist or not exist. So let's just hit it. All right, derivatives fail to exist when graphs hit a sharp turn. For example, the derivative of a graph with sharp turns, let's look at the absolute value of x minus 2. Sketch this graph and find the derivative when x is 2. And we know that absolute value function, this one's getting shifted to the right by 2. So I will have a vertex hitting there. And we have that shape, don't we? Okay, so there's our f of x function. F of x equals absolute value of x minus 2. Now, absolute value. Now, why is that the case? Why do we have to say down here at 2 the derivative doesn't exist? Well, the derivative is a limit notation or definition. So if I want to, I should be able to look at the limit as x approaches 2 from the left, and I should be able to look at the limit as x approaches 2 from the right of f of x minus f of c over x minus c. And if we do that in this case, I would have the limit as x approaches 2 from the left of absolute value x minus 2 minus f of c, which is 2. 2 minus 2 is 0, over x minus 2. And from the left side, I wanted to try and make that simplified. Let's do it this way. The limit as x approaches 2 from the left side, then I could use like a number. I'm not even going to do that. A number like 1.999. Take away 2, absolute value that. On the bottom, 1.999 minus 2. And what I notice is that I'll have the same difference on top as I do on the bottom. On the bottom, it's going to be a negative. On the top, it's going to be a positive. So this would come out to be negative 1. Not surprising that we're seeing the slope of that left side be negative 1, is it? We knew that actually before we probably even started. Here, if I do f of x from the right side minus f of c over x minus c, I would have the limit of absolute value x minus 2 minus 0 over x minus 2. Let's use a number, bigger than 2 as x approaches 2 from the right. If I use a number a little bit bigger than 2, that would be like saying 2.001 minus 2 absolute valued over 2.001 minus 2. And we get the same difference over the same difference, and positive divided by positive, so I'm going to get a slope of 1. Not surprising here that the slope is 1. So the derivative from the left, or the limit from the left that represents the slope of the line, the derivative at 2, and the slope from the right do not agree. So the limit as x approaches 2 of f of x minus f of 2 over x minus 2 does not exist. And for that reason, we can see that at a sharp corner, derivatives will not agree with that sharp sudden turn. If we had a parabola, we have that nice gradual turn, and then we're fine because the limits will agree from left and right, but not when you have that sharp point. The other place that this can occur, graphs with sharp turns, these can be like corners like we saw in the absolute value. They can also be cusp. And a cusp is more of a curved feel to it than a corner being like straight line linear coming into a straight line leaving it. So Cusp and corners are where derivatives fail to exist. Vertical tangent lines are also another place where we would have to say the derivative doesn't exist. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. For vertical tangent lines, it's possible to use this definition, and we would get this as h heads to 0. Well, then we're dividing by very small, and we could end up with either negative infinity or potentially positive infinity. And we know that that is a definition that describes a vertical line, and then the derivative doesn't exist. So vertical lines, as displayed by the shape of that graph that we're looking at. So example 2 says, sketch the graph and find the derivative of f of x where x equals 1, x raised to the 1/3 when x is 0. So let's look at let's draw the picture first. If you do it on your graphing calculator, when I have a very, very small decimal, this actually shoots quite quickly. I'm going to try and draw this in. It sweeps up at a very sharp rise there in that transition from concave up, bending over to concave down. So this is f of x equals x to the 1/3. At x equals 0, we can see that there is a vertical tangent line in there. And we could look at the limit as x approaches 0 of x to the 1/3 minus 0 to the 1/3, evaluating the limit at c, and then x minus c, which our c value is 0, gets us the limit as x approaches 0, x to the 1/3 over x. We would use subtraction rule to simplify those exponents. So that's going to give me 1 over x to the 2/3. It'll be positive in the bottom. Now, if I plug in 0, you can see how we're going to be dividing by 0. So if I come into 0 from the right, it'll get squared and be very, very small. If I do 0 from the left, it'll be negative, but squared, so that'll be very, very small positive. I'm going to have 1 divided by a small positive. No matter which side of 0 I come into, this is going to give us infinity. Okay, and therefore the tangent line does not exist. Derivatives that fail to exist, just pulling it all together here, derivatives of a function f of x at a point where it has a sharp turn or a cusp does not exist, or where it has a vertical tangent line, it does not exist. Highlight that or underline that in your notes. The activity here says, think of a graph and sketch 2 different functions f of x where the derivative fails to exist because of each region shown on the left. Well, the first one was the cusp or the corner. We already did the corner using absolute value, so let's go for one with a cusp. And I know a function that has a cusp. It's y equals x to the, I need it to be even, so I'm going to go 2/3. And that is going, if you graph it, you can go ahead and graph it, you will see that it has that shape of a curve coming in. So concave down, and then it meets at 0, 0, and then it leaves with a concave down as well. So that is a cusp. Cusp at 0. So the derivative of 0, I could show you a y prime of 0 does not exist. That y prime meaning derivative. Let's see. The other reason is the vertical tangent line. So they used x to the 1/3 before. What if we did y equals x to the 3/5? Then I'm going to pick up, it's going to be a little bit faster in its descending, but then it has that same quick vertical switch going on at 0. If I could get that to draw nicely in there. Yeah. Something like that. Put it in your graphing calculator, verify it. We end up with vertical tangent line. At x equals 0. So y prime of 0 in this case, once again, does not exist. The theorem below will become very important throughout the course by allowing you to apply other special theorems. So this theorem, differentiability implies continuity. If f is differentiable, if f is differentiable at x equals c, then f is also continuous at x equals c. So in order to be differentiable, it has to be continuous. If I had a gap, then I certainly don't have a derivative there. It has to be connected. We have to have nice smooth connections in order to draw a tangent line and say that a derivative exists. So differentiability implies continuity. Now, does the reverse work? Can it be continuous? The converse of the theorem, this is not true. This should say the contrapositive. I definitely, this is a true false. This would be false. That statement's okay. The converse to the theorem above is also true. That is not the case. Do you remember in geometry you had that if-then statement? If P, then it leads to Q. So if P is true, Q must be true. The converse does Q leads to P. And it says if it's continuous, then it's differentiable. That is not true. So this is a converse statement if this was your original statement. So this is not very often that you can just switch the words around and have it be true. Prime example is what we were just working with. How about that absolute value? It is continuous, but it's not differentiable at a certain point there at that corner. The converse says if f, we can do converse. If f is continuous at x equals c, then f is differentiable. I just want to make sure you know this is not true. If the converse is not true, sketch a function to the right that serves as a counterexample. This is my counterexample. So go ahead and put that. Let's say it's y equals absolute value x minus 2. So we're going to strike for 2 right there. Slopes of -1 and 1 on the left and the right. Yeah. The contrapositive is true, which says, do you have a spot? You do have a spot you could put this on. So the contrapositive in geometry was where it says if not Q, then not P. And as long as you negate both sides, then it's going to be true. So this would say if F is not continuous, then F is not differentiable. And that is true. So that one's true. This one here is definitely false. Good to know. All right, estimating the value of a derivative numerically, the table given below gives the body temperature in Fahrenheit over time in minutes of a polar bear on a very cold Arctic day. So his temperature starts at 98. Looks like it is decreasing, isn't it? Over 8 minutes is what we're looking at. So it says estimate the value of the temperature, the derivative of T at 5.5. So we want to come up with a way to estimate the slope of the tangent line. This means the derivative at t equals 5.5. So it says, recall that a derivative is really the slope of the tangent line at a point. So this problem is asking us to find the slope at 5.5. And you know what? I'm going to probably take out the word find, and let's use the word estimate, because that's the best we're going to be able to do on this problem. Let's asking us to estimate the slope at 5.5. Well, remember when we were working with these points, and we had this graph, and we said we have this point P and Q, and we want to bring Q closer and closer to P. So what I want to do is find a place on my chart where I'm very, very close to 5.5. And then I can calculate the slope of the secant line to estimate the slope of the tangent line. The tangent line being the line right underneath there at 5.5. So I'm looking over here at this. I can use the time value at 5 and the temperature value at 5 and the temperature value at 6 and get a good estimate of what 5.5 would be. So let's say T prime of 5.5 is about f of 6 minus f of 5 divided by 6 minus 5, which then turns out to be 90.45, take away 90.73 divided by 1, which turns out to be, I think I've got this calculated, 0.28. It's negative. Oh, that looks like a triple equality statement, which is negative 2.28. That makes sense that the slope is negative because we can see that the temperatures are decreasing, and a negative slope means we are headed down. So I like that. What would be the labels of this? Well, slope is a rate, and it's going to be the temperature, which was in Fahrenheit, so degrees Fahrenheit, over time is in minutes. So it's losing 0.28 degrees Fahrenheit every minute on average at time 5.5. Perhaps you can recall a very important theorem from algebra that enabled you to write the equation of a line. It was called the point slope form of an equation, and looks something like this. Highlight that. We will use that point slope form a lot. It's a very convenient equation of a line to write because all you need is a point and a slope. By simply renaming some of the values within that equation, we come up with a powerful tool to write the equation of the tangent line. So here they're saying the slope of the tangent line exists. If it exists, then the equation of the tangent line to the graph of f at some point C is y equals y minus f of c equals f prime of c x minus c. And that is really a takeoff of our point slope form. If you remember in algebra, we had y equals mx plus b, but that was always kind of a pain because you had to know b. An easier one to work with was y minus y1 equals the slope x minus x sub 1. And you can see how things cross over here. Our slope is found by using the derivative at a point. Okay? So, example 4. The graph of the function f given below consists of 3 line segments. Find f prime of 4. Okay, so I need to count out 1, 2, 3, 4. At 4, And then let's take and do a vertical line upwards. Doesn't look like I have a line tool offered on this. Okay, at 4. I'm just going to try my best. You know what? I'm off because this is counting by twos. I was thinking I was going to end up there at 6, and I didn't like that. It's because I didn't look at my scale first. Okay, so right there is 4. Well, what we're fortunate with is that we have a linear function. And on this blue line, the slope stays the same the entire distance from this point 0, 1 to this point 613. Why not just calculate the slope of the line? So f prime of 4 is going to be found by looking at the slope of 13 minus 1 over 6 minus 0, which gives me 12 over 6. Would you believe it has a slope of 2? At least it's positive. It's going in the right direction. Yeah, it's 2. So all along here, we have this slope of 2, and that means that f prime of 4 has a derivative that's equal to 2 as well. Nice, easy problem. Example 5, we got 2 to go. Example 5. The function f is defined on the closed interval -2 to 16. The graph of the derivative y equals f prime is given. So we're looking at the derivative graph. What does this graph represent? The derivative of f at different x values, right? So all I need to do is read the graph, and that is the actual slope for our original function f. So the points 14, -2 is on the graph of y equals f of x. So this is original graph, right? You got to really pay attention to the notation. This is the original function. An equation of the tangent line to the graph of f at 14, -2 is, well, I'm going to think of this y minus f of c equals f prime of c x minus c formula. And let's plug things in we know. So I know y minus -2 equals, I'll figure out the slope in a moment, x minus 14, because this would be c comma f of c, the original function, and a point on the original function there. Now, what is the slope at f prime of 14? Well, I'm going to go over to 14. 2, 4, 6, 8, 10, 12, 14. And I read this, and this says f prime of 14 is 3. The slope is 3. So, and it might be this one. No, because that's the wrong point, isn't it? It's this one. It's B, because this would turn out to be plus, wouldn't it? So I get y plus 2 equals the slope of 3, x minus 14. Not bad. If the line 2x plus 3y equals k is tangent to the graph of the original function f of x at the point where x equals 5, and the value of the limit f of x minus f of 5 equals what? So essentially what they want us to know, they called the function f prime of 5, get the 5 in there, is equal to the limit as x heads to c, or x heads to 5, of f of x minus f of 5 over x minus 5. How can I find that slope? Well, we do have an equation that says it's the tangent line. I'm going to write slope of tangent, because that's what a derivative is. Take our 2x our 2x plus 3y equals k, and let's solve for y. And I would have 3y equals negative 2x plus k, divide by 3. I've got negative 2/3 x plus 1/3 of k. Well, y equals mx plus b tells me what the slope of that tangent line is, right? Right there, I can tell that the slope was negative 2/3. What is the limit calculating? It's calculating the slope of the tangent line at a specific point at x equals 5. Okay, kind of a variety of things that we did there. Oh, the sheet's not showing up. I don't know why that is. But there's a worksheet for you to work on. It's the 2-4 one. It should be following your notes of what we just finished. Should be the next thing in line. There's page 2 of it, if that helps. All right, have a good day.